So hello everybody. This is my first video on number theory, and the first two or three videos will be on basic concept, extremely basic concept, which are prerequisites. We can say the basic primer that is required to understand this concept of number theory. So first two or three videos will be on extremely beginners level, even the problems, so that we can build up our concept uh, progressively, and it should be concrete. And then after that we'll get into intermediate level and then advanced level, so that we can touch some of the problems for international mathematics olympiad. So now, in the first two or three video lectures, what it will contain is I'll give you a brief idea of what is number theory, number and their types with examples, or also you call it divisors. It's the same thing. So somebody say factors, somebody say divisors. After it, same thing, and multiples, divisibility test rules, fundamental theorem of arithmetic and prime factorization form, the base of a number system, and common bases. So, what is number theory? Probably one of the oldest branch and most interesting branch of mathematics. Actually, mathematics is known as the queen of science, and the topic of number theory is known as the queen of mathematics. It's like that. Uh, it deals with properties of integers, at least in its elementary aspects, and more particularly or precisely, it deals with positive integers, that is 1, 2, 3, 4, 5, and so on. We know that there is no end to it after 5. And these set or this collection are also known as natural numbers. So this collection of certain things, similar things, we'll call it set is a mathematical term. So sometimes a group of similar things with perfect definition, with certain definition, they are known as a set. So this is a set of natural numbers. The natural numbers are known to us so long that the mathematician Leopold Kronecker once marked, God created the natural numbers and the rest is the work of man. And well said. So, now what are natural numbers? Natural numbers are the set of positive integers. We know it's 1, 2, 3, 4, and so on. They're the collection. This collection of the set is denoted by n, and it will be like n with a certain style. It's like a mark here, and also known as counting numbers or cardinal numbers, because these numbers are used for counting. Integers are the collection of all positive, and the other set of numbers we know it's known as integers, and they are the collection of all positive and negative whole numbers including 0, and they are denoted by this style list z. And in this collection, what we have, all the negative numbers from negative infinity coming towards positive side. It is then at some point will reach -3, -2, -1, 0, 1, 2, 3, and so on. And then we have the set of rational numbers. These rational numbers are all the numbers that can be represented as p over q, where p and q are both integers, q not equal to 0. And this, what we say, is GCD, the greatest common divisor of P and Q is 1. That means P and Q, they are co-prime. That means there is no common factors between P and Q. The only common factor is 1 because we know 1 divides any number. That means we cannot cancel out p and q any further. They cannot be reduced if they are put into fraction form. So p over q, that means if I say 4 over 6, then they can be further reduced. So they have common factors, which is 2. So you can further reduce them to 2 over 3. So now this 2 over 3 we cannot further reduce because 2 and 3 are co-prime. Co-prime means the two numbers which does not have any common factor other than 1. They are the greatest common divisor or highest common factor, HCF, is 1. And the greatest common divisor representation, which will come, it's a separate topic, is written in parenthesis p comma q, or in the first bracket p comma q equal to 1. This means that highest common factor or GCD is 1. They are co-prime. Now here p and q, we write it as p over q. Here p and q are both integers. That means they can be both positive or negative. But q should not be equal to 0 because in the denominator 0 means we are dividing any number by 0, and that is not defined, that is undefined, which I will explain in a later video. Maybe in the next video I'll explain why we cannot divide any number by 0. 0 in the denominator is illegal in mathematics because it is undefined. And so all the what to say, the integers, they can be written as p by q. For example, 5 can be written as 5 over 1. Actually 5 is what is there in the denominator. The denominator is 1, 5 over 1. Or minus 10, minus 10 can be written as minus 10 over 1, and so on. Minus 10 can be, so we can see that they are in the form of p over q. They are the ratios of two integers, and the denominator is not 0, so they are also rational numbers. And all the decimals which are either terminating means after decimal point they end at certain point. For example, 2.35, after 35 there is nothing, so they are ending. This kind of decimal are known as terminating decimal. They can also be represented as p over q. 1.66666, it's a continuous decimal, but one thing is it is non-terminating, but there is repetition of digits. 6 is coming after 6 and 6 and 6, so they are known as non-terminating but recurring. That means repeating, after decimal digits are repeating. So it can be one digit repeating, or in the next example we can see that it is 3.1232323, a pair of digits is repeating, or it can be 3 digits repeating, like that. So anyhow, if we see that there is a non-terminating decimal but a certain digit or a certain number of digits is repeating after a certain interval, that means they can be represented in the form of p over q, and they are rational numbers. So all the integers as well as all the decimals which can be written in the form of p over q, that means the terminating decimal and non-terminating but recurring decimals, they are rational numbers. Here we'll not talk about irrational numbers which are non-terminating as well as non-repeating decimals. For example, pi. Pi is a very well-known constant. We know that to find out the area of a circle, the formula is pi. Pi symbol is like this. Okay, pi symbol is like this, pi r square, where r is the radius. This is the formula to find out the area. Now pi is a constant. Constant means it has a fixed value, where r can change, the radius of a circle can change, but the formula is pi times r squared. But pi is an irrational number. That means it does not end after decimal, and there is even no repetition of digits, so we cannot catch after decimal, and therefore they cannot be represented in the form of p over q. So it's like 3.141592655 and so on, and there is no end to it. But for our convenience in calculation, we take the first two decimal place and we round it off to 3.14. And in some cases we take it as 22 over 7, because 22 over 7, three also the first three significant figures is 3.14. And then the square root of non-perfect square numbers. 2 is not a perfect square number because 2 is square of no natural numbers. So square root of 2 will also be an irrational number, that is non-terminating, non-recurring decimal. Cube root of non-perfect cube numbers. For example, 64 cube root is 4, but 4 itself is not a cube root, because there is no such natural number whose cube means multiplying the number with itself for 3 times. Suppose 4 cube is 4 into 4 into 4, 4 into 4 into 4, which gives you 64. So now if we do cube root of 64, we will get 4, but if we do cube root of 4, there is no natural number, because there is no such number whose cube is 4, whose cube is 4. So cube root of 4 will be an irrational, it's an irrational number, and so on. So, and also we'll not discuss about complex numbers. This is a separate topic which has a real number and an imaginary part, which is a different topic, which is a separate set of video. Maybe we can have a plan for it. Then moving from here, we'll know some more facts about number systems. For example, even numbers. We know even numbers are those numbers which are divisible by 2. These numbers, the unit digit, that the last digit must be either 0 or 2 or 4 or 6 or 8. So that means 42, 50, 50, 50, 24. These are all even numbers because their last digit is even, which is 0 or 2 or 4 or 6 or 8. If you see in the last digit, it is either 0 or 2 or 4, 6 or 8, they are even numbers and they are divisible by 2. The main point here, while solving problems, we need to consider a number, and if it is given even, then we'll consider the number to be as twice n, where n is a number, n is an integer. So if it's a natural number, then n will be any natural number from 1, 2, 3, 4. Because if you put n equal to 1, then 2n is 2 into 1, which is 2. If you put n equal to 2, then 2n is 2 times 2, or 2 into 2, which is 4. And if you put n equal to 3, then 2 into 3, it will be 6. So we'll get all the natural numbers, putting the consecutive values of natural numbers as n. So the general representation, this you have to remember, that always whenever we are considering some even number, we'll take its general form, algebraic form, as twice n. Similarly, odd numbers are numbers which are not divisible by 2. That means the last digits has to be other than even numbers. That means 1, 3, 5, 7, 9. So like 41 is an odd number, 53 is an odd number, 67 is an odd number, because from the last digit you can see that they are not even, so they are odd numbers, and odd numbers are not divisible by 2. And similarly, their general representation is twice n plus 1 plus 1. If you put n equal to 1, then 2 into 1 is 2 plus 1, it is 3. We'll get the first odd number. If you put n equal to 2, then twice n is 2 into 2, 4 plus 1 is 5. We'll get the next. So twice n plus 1 is the generator. This is the general form of odd numbers. You have to keep it in mind always. And one more thing, after every even number, the next number is odd, and after again the odd number, it is even. So they run one after another consecutively. Then we have square numbers. Square numbers are numbers which are square of consecutive natural numbers. For example, square of 1, which is 1, square of 2, which is 4, square of 2 square is 2 into 2, which is 4. We have to multiply that number with itself and we'll get the square numbers. 3 squared is 3 into 3, which is 9. 4 squared is 4 into 4, which is 16. 4 squared is 4 into 4, which is 16. So this 1, 4, 16, these are all perfect square numbers, all perfect square numbers. But we have to look here one thing. I'm sorry. You have to look here one thing, that in between 1 and 4 there are two other numbers, 2 and 3, but they are not the square of any numbers, because in between 1 and 2 there is no number. So 2 and 3 are non-perfect square numbers, and that's why if we do square root of 2, we'll not get any number, and the number that we'll get is actually an irrational number, which are surds, which are non-terminating and non-recurring decimal, which I've discussed a bit earlier. Similarly, between 4 and 9 there is 5, 6, 7, which are also not perfect squares, even 8. And that's all what we have an idea about what are square numbers and what are non-perfect square numbers. So for example, 20 square is 20 times 20, which is 400, which is a perfect square numbers. Perfect square numbers. Now 21 itself is not a perfect square number, but 21 square will be 441, which is a perfect square number. So that is the idea about perfect squares. And then triangular numbers, so very interesting numbers. These are the sum of first n consecutive numbers, and they are known as triangular numbers because they can be used to form a triangle. For example, I'll take 1 is the sum of first natural number. That means there is one natural number. First natural number means there is one number and its sum is 1 only. The sum of first two natural numbers is 1 plus 2, which is 3. 1 plus 2, which is 3. The sum of three natural numbers is 1 plus 2 plus 3, which is 6. 1 plus 2 plus 3, which is 6. And then we have 1 plus 2 plus 3 plus 4, which is 10, and so on. 1 plus 2 plus 3 plus 4, which is 10. They are, so we have 1 here, we have 3 here, we have 6 here, we have 10 here. But why they are known as triangular numbers? Because we can draw a triangle with so many points, with so many objects. So I have a one object, say I have a one dot. So one dot is can be shown as a triangle. Next, with three dots I can form a triangle. I can form a triangle like this. I can form a triangle with 6 dots. I can form a triangle. With 10 dots I can form a triangle. I'm sorry if I'm getting a bit, because I want to, oh sorry, explain here, that's why. So please bear with me. You can see that we can form triangles with this number of dots, and you can try by yourself. That's why they are known as triangular numbers. And one important fact I want to mention here, that sum of n natural numbers is given. You have to remember this formula, and I'll also, in the due course of time, I'll also give you some more important formulas, and we'll prove them in our induction videos. So the sum of n natural numbers is given as n into n plus 1 over 2 over 2. This is a very important fact which we need to know. We need to put it by heart, that whenever we need to sum the n consecutive natural numbers, the first n consecutive natural numbers, for example starting from 1 to 10, 1 plus 2 plus 3 plus 4 plus dot dot dot, like this. If you add up to 10, then either you can add and you will get the result, but quick way is, here how many natural numbers are there, here how many natural, first how many natural numbers, it is 10 natural numbers, so n equal to 10. So I'll put n into n plus 1, which is 10 into 10 plus 1, 10 plus 1 over 2. And 10 into 10 plus 1 over 2, that is 10 times 11 over 2, 10 times 11 over 2, 10 times 11 over 2, and then if we cancel out 2 and 10, it will be 5 here, 5 here, and 5 times 11 is 55. So if we add them, you will see that the result is 55. Similarly, sum of first 20 natural numbers, then n equal to 20. So 20 into 21 over 2. So that will be 210, because 20 and 2 will get cancelled. It will get 10, and 20 plus 1, it will be 21. So 21 into 10 is 210. So like this we can, but one thing you have to keep in mind, this has to be first n consecutive numbers from the beginning, 1, and then consecutive natural numbers. Then we have palindromic numbers, the numbers that remain unchanged when read from right to left. For example, 11. So if you read from proper way, which is 1 1, and from the back side also it is 1 1, it did same. Then 2 4 2, then 1 3 3 1, 1 3 3 1. So these are all palindromic number. That means whether you read from left to right or you read from right to left, it is unchanged. The number is same. So they are known as palindromic numbers, like palindromes in words. And then moving from here, it's a very interesting topic which we are going to learn here, which are perfect numbers. So what are perfect numbers? Perfect numbers are positive integers which is equal to the sum of its proper divisors. Proper divisors means suppose 6, and 6 is the smallest such perfect number. So what are the divisors of 6? So divisors of 6 are 1, 2, 3, and 6 itself. We know they are the divisors, but out of that 6 is not the proper divisor because it is the number itself. So this is not a proper divisor. So the rest are the proper divisors, and if we add them, that is if we add 1 plus 2 plus 3, we'll get that number itself. So this type of numbers are known as perfect numbers, and they are so perfect, that's why they are very rare. Their occurrence is very rare. 6, and after that we have 28. 28 is the next perfect number, and its factors are 1, then 2, then 4, then 7, then 14, and then 28. But 28 is not its perfect, because 28 is a number itself, so we'll not consider 28. We'll consider only the perfect divisors, and if we add them, we'll get 28 itself. Now some important facts on perfect numbers. That till date there are 51, only 51 known perfect numbers, and the last perfect number was discovered in Jan 2013, and we'll see what is that perfect number. I'll give it to you. And they're very so perfect, they're very rare and also very interesting. Their occurrence are thoroughly related to a very special kind of prime numbers, which we'll discuss later. They are known as Mersenne primes. What are primes? What are Mersenne primes? We'll discuss in this video only a bit later. Then we have a list of some perfect numbers, which are 6, 28, 496, 8128, 335,500, 333,550,336, and so on. The first four perfect numbers, which are 6, 28, 496, and 8128, was discovered by Euclid in 4th century BC. Until date, there are no known odd perfect numbers. All perfect numbers are even. So these are very important facts on the perfect numbers. And we'll come back to perfect numbers when we'll do a little bit on primes and Mersenne primes. But moving from here, we'll first discuss about prime numbers. So what are prime numbers? Prime numbers are actually the basic numbers, and actually the natural numbers are broadly classified into two types: either they are primes or they are composite. And prime numbers are the basic numbers, and prime numbers actually build the other numbers. So how they build the other numbers, we will see when we'll do the next theorem, which is fundamental theorem arithmetic. But what are prime numbers? Prime numbers are the numbers which are divisible only by 1 and itself. They don't have any other factors. Only the factors they have are 1 and itself. So we can divide the number only by 1 and itself. So the only even prime number is 2. There are no other even prime numbers. All other prime numbers are odd. And the next prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on. Okay, so we know that these numbers, we cannot divide these numbers with any other numbers. These numbers are divisible by only 1 and itself, but they mix other numbers. And there comes the theory of composite numbers and fundamental theorem of arithmetic. So what are composite numbers? All the numbers which are not prime are composite. That means they have at least one more prime other than one, at least one more divisor other than one and itself. So at least they have three divisors, one itself and at least one more. It can be more than one. So like 8 is a composite number. Why? Because we can divide 8 by 1, we can divide 8 by 2, we can divide 8 by 4, we can divide 8 by itself. So see, other than 1 and itself, it has two more factors, which is 2 and 4, and that's why it's a composite number. Now, the next theorem of this fundamental theorem of arithmetic is very important, and it states that every positive integer n greater than 1, because 1 is neither prime nor composite. 1 is known as a unit number. Okay, so every positive integer greater than 1, they can be represented as product of primes. So when you multiply primes with or without powers, it gives us a number, and that number, it's a uh, if you multiply different primes, then it will get a composite number. And for example, take any number. Let us take prime first. So 2 can be written as 2 to the power of 1. So it's a prime with the power 1. 3 can be written as 3 to the power of 1. 5 can be written as 5 to the power of 1. So all the prime numbers can be written as primes, and with some powers. But if we take a number, say 180, now I'll discuss with you a tool which is known as prime factorization. What is the prime factorization? We'll try to divide the numbers with prime numbers starting from 2, the list of the prime number, and we'll write down the quotient part only. If it is divisible by 2, I will continue to divide it by 2 until and unless it doesn't get divided by 2. Then we'll go to the next prime and check whether that number is divisible by that prime number, and we'll try to divide with that. So 180 divided by 2 is 90, and then 90 divided, again I can divide it by 2. So I'm writing only the quotient. 90 divided by 2 is 45, and then 45 cannot be divisible by 2, because we can see the last digit is 5, which is not even. Now, can we divide it by 3? Yes, there is a divisibility test rule part also in the next video session. We'll learn there. 3, it's divisible by 3 because the sum of the digits is 4 plus 5, which is 9. And so it will be divisible by 3. And we know that 15 times 3 is 45. So it will be 15 here. Now 15 is again divisible by 3. So we'll continue to divide it by 3 until and unless we can. So it will be 5. Now 5 is no more divisible by 3 because 5 is a prime number. So 5 can be divisible by only itself, and then here we'll end up at 1. So when we reach to 1, we will stop, and now we can write this 180 is what? 180 as the product of primes with their powers. So how many 2's we got? 2 into 2, which is 2 square. 2 square times 3 square, 3 square times 5. So all the numbers can be represented like this, can be represented as a product of the primes. with powers, with positive powers. Okay, and these powers are positive natural numbers. And so any number n can be written as the primes with their powers. This power can be 1 or any other positive natural numbers. Not necessarily all the primes has to be there. Okay, for example, in the above case 180, there is no 7, no 11. So if 7 is there, then it will be another number. So like this, some primes with to their powers and product of them. Any all the numbers can be represented in this way, and this representation is known as prime factorization form, which is very important. So this is about composite numbers, and this is a very unique representation. Only unique means one and only of this kind. There is no other form. In we can represent a number in prime factorization form, which is unique means only one form will have, one and only one form. That's all. And so from here, if we move on, we'll talk about now. Since you have learned what is prime, now we'll learn about some spatial primes, which are known as Mersenne primes, which was discovered by Mersenne in 1637 probably. And we found that there are some primes which are in the form of 2 to the power of p minus 1 minus 1, where p itself is a prime. But check, there are some primes, not all. P is a prime. What does that mean? P is a prime. So that means, for example, what is the first? 1 minute. I'm sorry. Sorry for that. So what does that mean? It means that if let's say p, what is the first prime? P is equal to 2. If we put here p is equal to 2, then we can check whether 2 to the power of p minus 1, which is 2 to the power of 2 minus 1, is a prime, and 2 to the power of 2 is 4. 4 minus 1 is 3. Yes, 3 is a prime. Yes. And then if we put p is equal to 3, we can have, if we put 2 to the power of 3 minus 1, 2 to the power of 3 is 2 cube, which is 8. 8 minus 1 is 7. Yes, 7 is also a prime. Then if we put p is equal to 5, p is equal to 5, then 2 to the power of 5, which is 32, and 32 minus 1 is 31, which is also a prime. Like that, if we move, we can think that yes, if we put all the primes 2 to the power of p minus 1, and if we put p as a prime, we'll get no, the case is not such, because moving on in that way, for example, when p is equal to 7, p is equal to 7, if we put 2 to the power of 7, which is 128, minus 1, which is 127, it's a prime number. Fine. And if we put p is equal to 11, p is equal to 11, then we'll have 2 to the power of 11, which is 2048. 2048 minus 1, which is 2047. This is not a prime. This is not a prime, and you can check there are some factors. One of the prime factors, I think it's 23, and it's a factor of 2047. So it's not a prime. So not all, putting all, it is not the case that if we put any prime p in 2 to the power of p minus 1, we'll get a prime, and that is the one. No, only some primes are there, p, such that if you put 2 to the power of p minus 1, we'll get a prime, and those primes are Mersenne primes. And those Mersenne primes are also few, and they are related to perfect numbers. And again, if we put 2 to the power of 13, if we put p is equal to 13, then 2 to the power of 13 minus 1, which is again a prime number. So we can check into that, which is 8191, I think. So we'll get 8191, and that will be a prime number. So we can get for some but it's few, not all. Now, how they're related to the perfect numbers, we can come to that part. So, the it was found that in the, for example, six, what are the factors that we add to get six? Because six is a perfect numbers, one plus two plus three, one plus two plus three, and then it's 28. 28 is 1 plus 2 plus 4 plus 7 plus 14 plus 7 plus 14, and then we have 496, 496, which is 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8 plus, these are all the factors of 496, plus 16 plus 31 plus 62, 31 plus 62 plus 124 plus 248. These are the perfect divisors of 496. 248, these are the perfect divisors of, and if you add them you'll get 496. The one thing to note here is that they all contains a Mersenne prime. See, 3 is a Mersenne prime, 7 is a Mersenne prime, and how we'll get 3? 2 to the power of 2 minus 1. How will get 7? 2 to the power of 3 minus 1. 31 is a Mersenne prime, 2 to the power of 5 minus 1. And even if you check and find out all the divisors of the next perfect number, 8128, 8128, we will see that 127, which is the next Mersenne prime, which is 2 to the power of 7 minus 1, is a divisor, perfect divisor of 8128. So there is a relation between a Mersenne prime and the perfect numbers, and later the relation was developed as such that if 2 to the power of p minus 1 is a Mersenne prime, 2 to the power of p minus 1 is a Mersenne prime, then 2 to the power of p whole thing minus 1 times 2 to the power of p minus 1. There is a difference in saying. While I say only, it may look same, but while I write you, this is 2 to the power of p minus 1. The power itself is p minus 1, but this is 2 to the power of p minus 1. That means I have to subtract 1 from 2 to the power of p, and their product will be a perfect number if 2 to the power of p minus 1 is a Mersenne prime. For example, p is equal to 2. We know it will give us a Mersenne prime. Let us put here p is equal to 2, and then we'll find 2 to the power of 2 minus 1 times 2 to the power of 2 minus 1, and from here I will get 3, because 2 to the power of 2 is 4 minus 1 is 3, into 2 to the power of 2 minus 1. 2 minus 1 is 1. 2 to the power of 1 means 2 only. So 3 times 2, which is 6, which is our first perfect number. Similarly, if you put let's say the next Mersenne prime, which you get by putting p is equal to 3, so 2 to the power of 3 minus 1 into 2 to the power of 3 minus 1, 3 minus 1. So 2 to the power of 3 minus 1 is 8 minus 1, 7, into 2 to the power of 3 minus 1 is 2 to the power of 2, which is 2 squared is 4, and 7 times 4 is 28, which is our next Mersenne prime. So with the help of Mersenne prime, we could have generated the known list of perfect numbers. And as a general knowledge, till that the largest Mersenne prime that was discovered, the largest perfect number that was discovered is it was in January 2013, and that prime is given as 2 to the power of 57,885,161, which itself was is a prime number. And if we put the value of p as such, that minus 1, I'm sorry, here I have to take a eraser. 161, 2 to the power of 57,885,161. This is the value of p. And then 2 to the power of p minus 1, then 2 to the power of this minus 1 is a prime number. Then if we put the value of p here, that means in that formula, 2 to the power of p minus 1 times 2 to the power of p minus 1, we got the largest perfect number till date, which is 34,850,340 digits long. That means this is not the perfect number, but the perfect number has these number of digits, so you can understand how big is that number. So that perfect number has, this is discovered in January 2000, that perfect number is this number of digits long. Okay, so we'll end because this session has gone very long, and in the next session we'll start with the factors, multiples, divisors, then some of the important facts about divisors and divisibility test rule and base numbers. So see you in my next video. Thank you.